I'm Ed Benjamin, and I work with Dr. Andrick this summer on the two-coupled metronomes project. The basic idea is that if you take two metronomes that have similar but non-identical frequencies and you put them on a board that's free to rock back and forth, the metronomes will synchronize. I'm going to show you a demonstration of this. That's what I was setting up. And I want you to pay attention to the amplitudes of metronomes and their phase relationship. I can describe it. Should I try exploring it?
Try refresh the page.
Vibration data presents.
Okay, so the metronomes start out of phase, and at the moment they are beating precisely against each other, so there's no coupling, the board isn't moving. But once they start to change their phase relationship, the board starts to rock, and it affects the amplitudes of metronomes. So you can see how the metronome on the left has a much larger amplitude than the metronome on the right. And then they begin to switch off, and you can see that the metronome on the right starts having a larger amplitude than the metronome on the left. You can also see how they switch between being in phase and not being in phase. If you pay attention, you can see how first one metronome has a very wild amplitude, and then the next time around will have a slightly less wild amplitude. You can also see that when they are in phase, they have the largest difference in amplitude, and when they're out of phase, they have a small difference in amplitude. Eventually, they have no difference in amplitude, and they are in phase. And at that point, they have synchronized, and they're going to stay that way until the springs wind down. Okay. So the reason we did this study is because synchronization is a widespread phenomenon that is difficult to understand, but we hope that by understanding this specific case, we can make general assumptions about synchronization itself. To do this project, we used a mathematical model rather than actual physical metronomes because we wanted to explore a greater range of parameters than were available in the real world. We are confident in our model because we spent the past 2 summers have gathered experimental data which fits the model quite well. Now, the heart of the project is the solution to this differential equation of motion. It is basically Newton's third law of triangular motion, where the acceleration equals the sum of torques divided by the moment of inertia equals 0. Here we have the angular acceleration term. Here we have the torque caused by gravity on the pendulums. And here we have the Vanderpool term. Metronomes are unusual pendulums because they have an escapement, which is a small device that gives the pendulum a little kick every time it passes through 0. The effect of this is to constrain the metronome to a particular amplitude. Here we have the coupling terms. Metronomes synchronize because they are coupled, and that's because the metronome and board system has a center of mass that stays still, but the center of mass of the pendulums oscillates back and forth. So the center of mass of the board has to oscillate back and forth. This means that the pendulums affect the board, and the board affects the pendulums. The reason why there are 2 coupling terms is because the board has a rocking motion in the x direction and a flexing motion in the y direction. This left us with 4 parameters. We have delta, which is a measure of how close the natural frequencies of the metronomes are. We have mu, which is the strength of the Vanderpool term, or how constrained the metronomes are to a particular amplitude. We have theta naught, which is 1/2 that particular amplitude. And we have the coupling constants, beta, which is how much the metronomes talk to each other. This is a basic solution to the equation of motion. You can see how there is a short timescale behavior, which is all those lines, which is every individual oscillation of the metronome. You can also see this long timescale behavior, where you see that first one metronome has a small amplitude and the other metronome has a large amplitude, and then they switch off. I'm going to show you the envelope for the top half of this graph. You can see how the amplitudes switch off until finally there's no change in amplitudes and the metronomes have synchronized. Because we are in a nonlinear system, changing the amplitude leads to a change in the frequency or period length. Here you can see again that the metronome with the small amplitude has a small period first, and the other metronome has a long period. And can see how they switch off until they wind up with an identical period length, which means that they are synchronized. A similar thing happens with the phase difference. The metronomes start 1 pi out of phase, and then they get in phase and out of phase, and in phase and out of phase, until finally they synchronize in phase. Now, how can we characterize this motion? You'll notice that it looks like a damped harmonic oscillator. So what we can look at is the period length. So we can see how quickly the metronomes switch off from being in phase and being out of phase. And we can look at the decay envelope, or how quickly they synchronize. We found that 3 parameters affect how quickly the metronomes switch off. We found that both beta on the left and beta naught affect how much they switch off. Both of these are behaving like coupling terms because when you have a large theta naught, the pendulum amplitudes are larger. So the center of mass of the pendulums moves more, so the board moves more, so the pendulums are coupled more. The reason why coupling the metronomes increases the rate at which the metronomes switch off is because you need a small phase difference has a large effect. If you remember the phase graph, the metronomes have to get to a certain phase difference before they will turn around. If you have a large beta or theta naught, you only need a very small phase difference for them to turn around, so the period length is shorter. Mu has the opposite effect, has a complicated effect. You can see how it's asymptotically going off to infinity here. That's because when your mu is equal to 0, the metronomes don't synchronize at all, so your period length is infinite. However, once you have a sufficient mu for the metronomes to synchronize at all, increasing mu means that the metronomes switch off more slowly. That's because the metronomes are constrained to a particular amplitude. So the metronomes don't want to have a large difference in amplitude, which means that if you go back to the phase graph, at this point, the metronomes have their smallest difference in amplitude. So the metronomes want to stay there, so they won't turn around as quickly, which would increase the period length. Then we have the envelope. We found that the same 3 parameters affected how quickly the metronomes damped. We found that if you increased beta, you decreased the decay constant, which means it took longer for the metronomes to synchronize. If you increase how much the metronomes talk to each other, then the priority for the metronome is what the other metronome is doing. The other metronome is oscillating, so it will keep oscillating, which means that it takes longer for the metronomes to synchronize. However, if you increase mu, which is how much the metronomes are constrained to a particular amplitude, their priority is having one particular amplitude, so they will synchronize quickly. Theta naught behaves like mu in this instance because the greater your theta naught, the more nonlinear your system. The more nonlinear your system, the greater percentage of the time the metronomes spend not at their goal amplitude. The more they spend not at their goal amplitude, the greater the contribution of the Vanderpool term, and so it's like increasing mu. Some things we might want to look at in the future are finding a simple algebraic solution to the differential equations. We looked at several options, and while there were good approximations of the quantitative behavior, they were not very good qualitatively. We also are interested in looking at non-symmetric systems, such as 2 non-identical metronomes, but similar frequencies, or looking at what 3 metronomes would do. Questions?
Can you go back to the envelope slide? Maybe something with the back.
This one?
No. The one with the go back. That one.
This one?
They're ending up at different amplitudes there?
Yes. The 2 metronomes have different natural frequencies. So one metronome will, so in order for them to have the same final frequency, they have to have slightly different amplitudes from what they would prefer. Because changing the amplitude would change the frequency.
So is what you said that this parameter beta, which you call the coupling constant, if it gets larger, it takes longer for the 2 to synchronize?
Yes.
That's the opposite of what I would have just guessed.
Well, because the two metronomes are oscillating, so they act kind of like forces on each other. So the more beta is, the greater effect the metronomes have on each other. So one will be getting to the right amplitude, but the other metronome will push it and it will get off again.
Are these plots that you show with arbitrary units? In other words, would they have the same form if the amplitude were meters instead of centimeters, let's say?
Well, these are in radians, so
Or even periods, for example. I'm just thinking if you had a huge metronome, how would that change the look?
I don't think it would as long as everything were scaled up with it.
It's a dimensionless time, so
Oh.
all of that's been scaled.
Okay.